So what we see here is that we got 3 sine squared plus 4 sine x in the denominator, and so this is kind of similar to what we saw when the first example of u sub that I showed you on Thursday. What might we how might we set u equal to here? Allison wants sine x. And this turns out to be a really good choice. So the question is, how do you know? Well, you know by experience, or else you try something and see if it helps, and if it doesn't, you try something else. Okay? So we're going to start with u equals sine x. And then we know we're going to need dx. So we don't want to solve for x and we get inverse sine. We don't want that. So what just happened? Okay. So let's just take du. What is du then? No, derivative of sine. Cosine x dx. And now notice something. Look, cosine x dx is equal to what? Du. There it is. You have du right there. Du is cosine x dx. So this is rigged, right? So this thing is du, or 1 over, what, 3 u squared plus 4u du. How do we handle that?
Factor out the u.
And we want to do that because, Joseph?
I wanted to set up a partial fraction.
Yep, so for partial fractions, remember, we need a denominator that factors. We need a denominator that factors. And so if it's going to be partial fractions, then 3u squared plus 4u has to factor into a product of 2 things, and it does. U times 3u plus 4. So I think now we're home free. So we're going to work this out, and we're going to get something over u plus something over 3u plus 4. Can you do it in your head? Can you do this one in your head?
Yeah.
What is it? Tell me what it is.
3 plus 4 plus, no, sorry, I need to calculate.
Do you need to do something? Okay. We need to get 0.
3 plus b equals 0, equals to 1, not equal to 4, equals to 1, a equals to 1 over 4, and b equals to negative 3 over 4.
All right, let's see. Boy genius here. 3/4, negative 3/4, and 1. Good. Good job. Okay. So that when we work it out, we get this. And I think we're home free, right? So this is going to be 1/4 natural log of u, and u is sine x. And then negative 3/4, we'll need another 1/3, right? So it'll be negative 3/12, or negative 1/3. Just write it out here. So 1/4 natural log of absolute value of sine x plus or minus. We're going to have negative 3/4, and then we're going to have 1/3 natural log of 3 sine x plus 4. And they're giving us the plus c in this problem. So the plus c is already given here, so we're not going to put it in the entry box. Let's see how we did.
It's plus.
Did I make a mistake? Oh, I had 2 minuses. But it did a double negative there. Yep. We got it. Questions on that one? Okay, let's do 7. Okay, so I guided you towards the table, but you actually, there is no table. Well, maybe there is. So Ruth said she used a table, but let me show you how you don't need a table for this. So what might be our first choice for you to start off? What might we try here to make things, to be consistent with the way we did it before and maybe make things easier? Yeah, remember when we had those sums and differences under radicals? By making that just all one thing, that allowed us to multiply, right? Multiply a radical as, say, like u to the 1/2. So if we let u equals x squared plus 25, then what do we have? So we need to get, so du then is 2x dx. Now here's kind of the trick you have to recognize. So it's kind of like the last one. Look, here's x dx. X dx is du over 2, right? So we can steal one of the x's from the x cubed to make x dx. And that works because what's left? X squared, which you can easily get from this. You see? So we can rewrite this as 0 to 5. So x squared times x squared plus 25 times x dx. So I just pulled that x cubed apart into x times x squared, and I gather that x with a dx. And so now what is x squared? It's u minus 25, right? So x squared is u minus 25. What is this? That's what we wanted to make easy, right? Square root of u. And then what's x dx? Du over 2. So since we never did, so let's go ahead and change, since we have a definite integral, let's go ahead and change the limits into the limits of u, and then just solve it and never go back to x, right? Since it's a definite integral, we can change the limits to u and just evaluate it that way. So when x is 0, what is u? 25. And when x is 5, 50. So u is going to go from 25 to 50. And so now all I have to do is find this value, right? This is a value, because that's what? The total change of a quantity as u changes from 25 to 50 at this rate, right? At this rate. U minus 25 square root of u over 2. And then we know what to do here. So we can do 1/2. And this was what a lot of these, what happened with a lot of these is now with the single term under the square root is we can now multiply. And so we got u to the 3/2 and minus 25 u to the 1/2. So 5/2, 2/5, u to the 5/2. Check my math, I'm going to go fast. 2/3. Check my math. Did I do the math right? I think so. So can we do the next step in the answer box? Here we go. We'll plug 50 in. It's going to be 1/2 times. We'll plug 50 in. So 2/5 times. I think square root. I think this is 5 to the 5th, because this is the square root of 50. Oh no, that's not right. That's not right. Let's just do it. So 50 to the 5/2. Okay, minus 50/3 times 50 to the 3/2. Okay, then minus, plugging 25 in, 2/5. Now this is what I wanted to do here. So 25th square root of 25, so this is 5 to the 5th. Right? Because this the half is the square root of 25, which is 5 raised to the 5th power. And then same thing here, be 50/3 5 cubed. I think that'll be plus, right? We're doing minus now, so then this is going to be minus and minus. So plus 50/3 times 5 cubed. And bracket for the 1/2. What do we think? Did I type everything in right? Did I do the math right?
That's good.
You just trust me, or did you really check? Got it. So this one, you had to, it's kind of this. There's this kind of this trick that you have to kind of recognize. Since our u is based on x squared, so let's get x squared separated, and then x dx is nicely what du is. So it's kind of rigged. It's rigged if you recognize that you're doing u based on x squared. So get an x squared, which easily is now u minus 25, leaving x dx, which is basically your du. Questions on this one? Can I erase it? Okay, cool. So, did you say 11 and 13? What else do we want to do?
Yeah.
Okay, 11. All right, so the first thing with this is that you got this negative infinity to infinity. So to handle this, we can still do one limit. We don't have to do like a limit to a and a limit to b. We can still just do one limit to a, and then have the integral then from negative a to a. So as a gets very large positive, then negative a will get very large negative. That's what we want. And then, of course, a. All right, so we got x to the 4th. Okay, so we're ready to do antiderivative. What's the antiderivative? Or what technique are we going to use? So we're starting to build it, or we have built a whole toolbox. So you have to have all those different techniques at your fingertips and recognize what's what. And so what are you applying there? What are you doing? She wants to do undoing chain rule. Does undoing chain rule work? Yeah, because you've got the interior function, x to the 5th. You've got its derivative, essentially its derivative, x to the 4th. So you're doing antiderivative of e to this, right? E to this, which is e to that, right? Antiderivative of e to the something is just e to the something. So when we do the derivative, we're going to get negative 5x to the 4th. So what do we need to negative 1/5? We're going to need a negative 1/5. So if we took the derivative, we'd have exactly that rate function we started with. So this is kind of, when I led you through that structure of undoing the chain rule, like first attempt and derivative check and then second attempt, a goal is just kind of to write them down now. I mean, the whole point of that was, as you keep practicing this, you can just write down these antiderivatives, like think it through, like what we just did, and just write down the answer. Okay. So traditionally, all these undoing the chain rule problems are done by use substitution. Like that's the way it's traditionally taught. The textbook teaches that, but doing use substitution would have taken us 3 times as long than just reasoning and writing it down. So that's why I wanted you to practice that and get good at it. So you don't have to spend all the ink and all the time working through use substitution when you can just recognize that that's just a chain rule, and we're just going to figure out what function has that as its derivative. So then we're going to go from negative a to a. So I hope for a lot of you that you found that undoing the chain rule, you're coming better at it. With more practice, you're getting fast at it, like we just did. Okay, so we're going to limit as a goes to infinity. And so we're going to plug in a and negative a. So we have the limit as a goes to infinity of negative 1/5. So what we're going to do is change this so it's a little bit easier to see. e. So put this in the denominator, right? E to the x to the fifth, positive in the denominator, right? Oh, a. Sorry, a. So then it'd be plus 1/5. Now I think here it's going to be, right, so negative of negative a to the fifth. Well, negative a to the fifth, since that's an odd exponent, that's going to be the opposite of a to the fifth, and then we're going to take the opposite of that. So this is going to be the numerator here, e a to the fifth. So did you catch all that? So e to the negative a to the fifth. That's what we're working on there. Is e to the negative a to the fifth, which is e to the a to the fifth. Now, if this were, so now what would it be if this were an even exponent, right? If this were an even exponent, what would we get in the end? We'd have a negative, right? Because the even exponent would make that negative go away, and we'd still have that negative. But with the odd exponent, it still ends up being a negative number. Taking the opposite of it, it's positive. So then this is e to the a to the fifth. So now the limit as a approaches infinity, well, that goes to 0. Really big denominator, right? As a gets really big, positive, we get a huge denominator that goes to 0. This goes to. So the fact that this goes to 0 doesn't help this at all, right?
But if the exponent of a was even, then it would be 0.
If it were even, right. So if that were to the sixth, then we would have gotten, this would have been negative a to the sixth. This would have been down here, and they both would have gone to 0, and it would have been convergent. But not convergent to 0. Something's wrong here.
Because I got a.
Yeah, it would be because it would be, yeah. So let's look at the graph of this rate function and see what's happening, okay? So let's graph that rate function and see what's happening. Questions on the math? Questions on doing the antiderivative and the limits? Did you follow it? So if I graph that rate function, what was it? X to the sixth. Was it sixth?
X to the fourth.
Fourth, thank you. E to the negative x to the fifth. So if we're integrating from negative infinity to infinity, look what happens as you get very, very large negative. That rate just gets huge positive. So if we're integrating, I mean, thinking about your rate of change going in the negative direction just becoming hugely positive, this is totally divergent. Now, if we integrate from 0, to infinity, that would converge. But we're not. We're integrating from negative infinity to infinity. So the problem lies here for x getting very, very large negative. This rate of change just whirls off to infinity, so our accumulation could never possibly converge. But when x is positive, that's not going to be a problem. This will definitely get to 0 fast enough. So if this changes to, we said if this changes to, say, 5 and 6, what happens? The total accumulation is 0 because you're going to have a negative amount of accumulation, right? This is rate of change means decrease, negative rate of change, and then positive rate of change. So that's why if the exponent is even up there, that whole integral became 0 because you'd have the negative accumulation and the positive accumulation canceling out. Okay, questions on that one? All right, and then 13. Okay, so this one. So we have to recognize, kind of see what we have here. We have 1 plus x to the 6th. And we kind of have to see that that's kind of like an antiderivative that we know. So we can't, so first of all, we can't do partial fractions because this doesn't factor. Long division is not going to work because the denominator has a greater degree than the numerator. So we have to kind of recognize 1 plus x to the 6th is kind of like an antiderivative that we know. What is it? Arctangent. If this was 1 plus what? Something squared. So we're going to do substitution, and we want it to, and in the end, we want it to be 1 plus u squared, right? And then it'll be arctangent of u. So if u squared, we want, in the end, we want u squared to be x to the 6th, then what are we saying u is? X cubed, right? U equals x cubed will give us 1 plus u squared in the denominator. So we do our du equals 3x squared dx, and lo and behold, look, x squared dx, x squared dx. What does x squared dx equal? Du over 3. So we can set this up as the limit as a goes to infinity of negative a to a, 5 times 1/3 du over 1 plus u squared. And now we've got it because we know that this is going to be 5/3 what? Arctangent. As far as the antiderivative, we've got it. We've got a limit to deal with now. So a to infinity, we got 5/3 arctangent u. And that's from negative a to a. So we're going to have 5/3 arctan of u, or a, sorry, minus 5/3 arctan of negative a. And so we have to know something about arctangent here. So as we're saying is arctangent, the input into arctangent is slope and output is angle. So we're saying we're going to let the slope of the terminal side in the unit circle get really, really large positive. Well, where is that? Where does it get really, really large positive? Pi over 2, right? So as we just let that slope get as super, super big, we're really saying it's going to be then the angle, which is the output of arctangent, is going to be indistinguishable from pi over 2. So this is going to go to pi over 2. And then as we let the angle get, as a goes to positive infinity, this angle will get ultimately big negative. That's down here. So we're going to let the angle get ultimately big negative. The limit is negative pi over 2. So we get 5/3 pi over 2 plus 5/3 pi over 2. It's going to be the total accumulation of this thing from negative infinity to infinity. So we're going to get 2, or 5/3 times pi over 2 plus another 5/3 times pi over 2. Okay, so I kind of talked through that fast. If I lost you, please ask. Did I lose you anywhere along the way there?
Just 1 times pi over 3 is pi
Sure,
over 2.
sure. I just wanted to write it in a form that is similar enough to that so you wouldn't. Yeah, you're absolutely right. But remember, Weber can be your calculator for you. So let's graph this rate function, and let's see that we get a positive accumulation from negative infinity to infinity. We get a positive. Let's see that. Let's see that. Where did I do that? So was it x? Tell me what the rate function was again. x
5x
5x squared.
over 1 plus x to the 6.
So that's that function. So we see that starting at negative infinity and accumulating, we always have a positive rate. We always have a positive rate. And then we know if we got a convergent integral, then what about how this rate approaches 0? What can we say about how this rate approaches 0? Quickly or not so fast? And likewise on the other side, how does this rate approach 0 if we ended up with a convergent amount of accumulation?
Goes away from 0 initially.
What's that?
It goes away from 0 initially and then comes back to it.
No, I'm talking about how does this rate function approach 0 as we get very large positive and very large negative? Not very fast? Or
Wait, it's convergent so very fast.
yeah, it's convergent. So because it's convergent, it must be the rate must be decreasing to 0 at a high enough rate. It must be decreasing fast enough so that the accumulation levels off, and that's happening on both sides now. It's happening on both sides. Remember 1 over x or 1 over x to something less than 1 doesn't converge fast enough. It gets to 0, or its limit is 0, but because it's heading down at a slower rate, the accumulation keeps growing, right? So this one, since it converges, it must get to 0 at whatever, it's fast enough, right? It must get there fast enough for there to be convergence, and that's on both sides. So then we get the bulk of this accumulation, though. We get the bulk of the accumulation here in the middle, right? So between, say, -3 and 3 is where we're going to get most of the accumulation because that's where the rate is more significant. But that rate has to get down fast enough to 0 on both sides for that integral to converge, right? For the accumulation to be a finite amount. Okay, we got written homework too, right? So name and date. Make sure you name and date on it. And what was that function? As you're passing it in?
2x squared over x squared plus 1.
Pass it to your left.
Yeah,
And what do we think? So here's the rate function. So accumulation, converge or diverge?
Convert. Diverge.
Oh, I heard some people say converge, some people say diverge. Do I have them all?
No.
Does the accumulation converge or diverge? It converges to 2, right?
The rate of change.
The rate converges to 2. So then every time a unit goes by, what happens to the accumulation? Okay, but what happens every time the x increases by 1? Every time x increases by 1, the accumulation does what? Increases by 2, right? That's what rate of change of 2 means. For every one, or that's one interpretation. For every one increase of x, the quantity is increased by 2. So, convergent or divergent? Divergent. Badly, right? Badly. So what did we say was necessary for convergence? The rate has to do what, first of all? Has to go to 0. But then in addition to that, it has to do what?
Go to 0 fast.
Has to go to 0 fast enough, right? So that the necessary condition is that the rate will go to 0, but that's not sufficient. It also has to get to 0 fast enough. So this doesn't even go to 0. So this is converging on 2. So it's basically like, in the end, it's just a constant rate of 2. So your accumulation is going to increase by 2 every unit. Just keep getting bigger and bigger and bigger. And so then you were to show that so you set up an integral and you show that you get a divergent integral, or your limit will be infinity if you do that correctly. Any questions on the written homework? And then that antiderivative, we're going to start with what? We got x squared over 1 plus x squared. How are we going to do that antiderivative? Yeah, that's right. So it's a rational function where the degrees are equal, right? And so you can start with long division. And I think you get arctangent again on this one, right? If you get something like 1 plus arctangent.
1 minus.
Or 1 minus 1 over, okay, 1 minus 1 over 1 plus x squared. And then you're going to have x minus arctangent. Arctangent is fine, that converges, but that x is going to diverge, right? You're going to end up with, your accumulation function is going to be, wrong, oh no, but anyway, so the accumulation function is going to be x minus arctangent of something, and the x right there, that makes it diverge, right? So as you go to infinity, x is just going to get infinitely large. Or 2x, I'm sorry, 2x. Okay. So let's continue. And then you saw the first half of some review exercises for exam Thursday. And that pretty much, that sheet covers everything we've covered up through the improper integrals. Make note of the ones that you're not responsible for. I put a list on Blackboard. So some of those stuff we didn't cover. So make sure you're not spending lots of hours on those problems that you won't need.
Do you have an answer sheet for those?
I don't, but we can in office hours. If you have so you can do Wolfram Alpha. You can test them out. You can email me if you have a couple you want to know answers to. We can work them out in office hours. So you got lots of ways to check with each other. But actually, now that I think of it, I might. So if you remind me, I can look for it. I might have it. But you got lots of ways to check your work. And all those antiderivatives, how can you check? Take the derivative. So that means you have to be good at derivatives too. But that's been how we've based our antiderivatives anyway, is based on knowing how to take derivatives.
Can we take cheat sheet during the
No.
so the table.
So okay, in terms of the identities, the trig identities, what I'll do is I'll give you. Let's see if I can find this. Wow, it's not happy here. Something's not happy. Here we go. Let's see. Let me show you what I'll do in terms of the trig identities, because those are most of the formulas. Okay, here we go. There, must be here. There it is. Okay. This is what this will be the first page of your exam, and so it'll be that identity sheet that did I ever post that for you?
You wrote it out.
I wrote. Yeah, so I said I was going to post it, so sorry that I didn't. You can always remind me of things like that. If I tell you I'm going to do something and I forget, just send me an email. But I'll post this filled out the way that I had shown you in class, and then the first page will be this. So you'll start exam by just writing them all down, and then I'll give you like a bonus point. I'll give you 1 point of extra credit for having those correct, and then you'll have those formulas for the exam. So it's kind of a compromise. So like I want you to memorize them, but let's just memorize the whole sheet. This would take you 10 minutes to do this correctly, to learn these and write these down. So and then I'll give you a bonus point for filling those in correctly, and then you'll have them for the exam. Okay, is that fair compromise?
Yeah.
But besides that, no other formulas will be given, and no crib sheet for this one. Okay. And then so then today we're gonna today and Tuesday and Wednesday we're gonna talk about area and volume, and that will all be on the exam as well. Okay. So it's kind of the trade-off of this. Of we're having one less exam here in the summer, one less hour exam. That means more material on each one. So this is a fair amount. That's why I wanted you to get started on your studying for what we've done so far. That's why you have the part 1 of the review sheet.
Is the test going to be in class?
Yeah, it'll be Thursday's class.
Does it start as usual at 10, 11:30?
So I want you to have 90 minutes. So what is 90 minutes? 10:40? No, 11:40. 11:40, right? 11:40 to 1:10. So we can answer a couple questions, 5 minutes of questions at the beginning, plus all the office hours before that. We can spend reviewing and answering questions, and we'll start about 11:40. So you have 90 minutes.
Is it 90 minutes and then pencils down? Go.
No,
Okay.
but I don't want to be here at 1:45 or 1:30. I get hungry after class, so I want to go eat.
If we have a question about tables, we are dating something about.
Yeah, if there's going to be integrals that you need tables, then you'll have the table or a partial list of the table. Yeah, of course. You don't. The whole point of tables is you're using the tables. You're not doing memorization.
I'm not sure if we learned this over the beginning of the course, but are there extra credit opportunities?
If there are, I'll announce them for everybody. It'll be something everyone can achieve or can get. But the thing is, extra credit can only affect your overall course grade at most maybe 1% or a little bit more than that. It's like exams are like 13 to 15% of your grade. So the real credit that you earn in the course is on the exams. Okay, that's going to be the biggest chunk. So extra credit can't raise your grade a whole letter grade. It could, if you're on the border between 2 grades, it could push you up. So put your stock in the studying for the exams rather than extra credit. That's what I'm saying. But if there is extra credit, it will be offered to everybody. Yeah.
In the test review, if there are any questions, then we need to use a table to solve it in the first part.
Yeah, there's some table questions. There's some that refer to using tables or like they give
in the first part. There are 21.
maybe.
Yeah, there are some. I went through
In that
last
first
time.
bank?
There are some that are kind of difficult, but it doesn't tell you to use tables.
Right. Most of the ones that we use tables for are going to be like this form. This is when you have some stuff that involves this, that's kind of a clue that maybe it's going to be tables. Okay. All right. So let's talk about. Talk about an alternative understanding of integrals. So what did we do? So over here I'm showing you a rate function here on the left. And say we wanted to find the total accumulation from 1 to, say this is 4.2. So how can I write an expression if this is the rate function is r of x? How can I write an expression that will give me the total accumulation from 1 to 4.2 at the rate r of x? Everyone should be able to write an expression like that. Alvaro, tell me.
I was thinking of like f of 4.2 minus f of 1.
Okay, so but I've got r of x. I don't have f or something. So if I'm going to use r of x, how would I do it using r of x?
From 0 to 4.2 of r of x dx.
So she's talking about an integral. Are we going to need an integral to do this? From what to what?
1 to 4.2.
R of x dx.
So we worked hard on that in the first couple classes, right? This meaning for integral or definite integral. Total change of a quantity from as x changes from 1 to 4.2 at this rate, right? At this rate, r of x. And so over here, if we tracked that accumulation starting from 1, it would be 0 at 1, right? And then according to this rate, it would grow. And then when we got to 4.2, it would be whatever this amount is, right? So that would be equal to this if the accumulation resets 0 at 1, right? So if at 1 we say we're going to start accumulating at 1, then it'll be 0, and then whatever we get at 4.2 would be that. Now if at 1 it was some other value, then we would have what? So we would have the final value minus whatever starting value we had, right? So the total change of the quantity using the rate, total change of the quantity using the quantity function. So f of 4.2 minus f of 1. That was what Alvaro was saying. But in this particular view of it, at 1, we're starting at 0. So this is that amount of accumulation right here. That is it. Okay, so what we notice is that what are we doing? We're summing up all the little changes in y, right? This is a little change in y, dy. That was our first tenet of the fundamental theorem, was that constant rate of change is modeled by a change in the quantity is the rate times the change in x. And so if we look at this here, we notice that the rate, what, is like this vertical distance, right? Say the first rate is this vertical distance, and then the change in x is this horizontal distance. So when we take that rate times that horizontal distance, we can see that that is, we'll also calculate the area of that rectangle. Do you see that? Because our rate is the vertical coordinate, and the change in x is a horizontal change. So then that calculation mimics the area of a rectangle calculation. Base times height, right? Base times height. So similarly, the next one would be the same base, delta x, times the new height for the rate number 2. And so on. Okay? So that integration is remotely related to area of rectangles is entirely an artifact of the fact that we graph in rectangular coordinates. The reason that this works is because of graphing, x on the horizontal axis and y vertically. And so it's kind of like coincidentally that calculation of r dx is also the calculation of an area of a rectangle. But it's only because of the way we've set up our graph, the way we graph, right? The way we graph in rectangular coordinates at 90-degree angles to each other, that we get this alternate version where r dx is also base times height. So that is not a deep principle, right? Rate of change in accumulation is significant. And then kind of as coincidentally, as an artifact, we get this kind of this area analogy. So what happens when we use more smaller intervals? We're going to get thinner rectangles whose tops match the rate function better, right? So when we use more thinner rectangles, the tops of the rectangles are going to do a better job at matching the curve, just like our pretend rate function did a better job of matching the curve. So now the tops of these rectangles do a better job. And then ultimately, for like infinitely thin rectangles, we're adding up the areas of these sticks, right? And so the result is that we have an alternate understanding of integral as area between the curve and the x-axis. But that's kind of superficial compared to rate of change in accumulation. This is superficial because, like I said, if you graph in a different coordinate system, well, then this all falls apart. If you have a different way of graphing other than x horizontal and y vertical, which is a man-made invention, then this idea of using areas of rectangle would all fall apart. It wouldn't. But rate of change in accumulation is always the meaning for integral. Okay, so let's just review the two versions. So now I'm showing little f, the function little f is our rate function. So if f of x is a rate of change function, then what does, so we'll just say from a to b. So then what does the integral from a to b f of t dt represent? If f, we think of f as a rate function. Accumulation from a to b at the rate f of t. Okay, so the accumulation of the quantity with rate f as x goes from a to b. All right, so now our new alternate understanding, so that's that amount of accumulation. All right, and the new alternate understanding is that f could be any function. It doesn't have to be a rate function anymore. It's any function displayed in rectangular coordinates, not necessarily a rate. Then what could that represent? The accumulated area between the x-axis starting from x equals a to x equals b. So again, now this f, when we're talking about area, it doesn't need to be a rate function anymore, but it's analogous to what we were thinking of as the rate function. But it doesn't have to be. It could be any function, and then that integral could also be, integral from a to b would be that amount of area that's shaded there as the result of not the sums of little bits of accumulation, but the sums of these areas of these sticks, like really thin rectangles, super thin rectangles, a gazillion of them. So in this course, you have to be fluid. You have to see it both ways. You have to see integrals both ways. You have to see them as summing up little bits of change given the rate of change. Version 1. You have to see them as summing up areas of super thin rectangles to get a total area. So this week we're going to be focusing on number 2. So this is more like the geometry aspect of integrals. How can we use them in geometry? So initially we can see them as areas by summing up these super thin rectangles across. And that's the area captured below the curve to the x-axis. Okay, questions about that? And so that area version is maybe what you're more used to from Calc 1 if you didn't have me for Calc 1. So integral is area. Okay, so just to review, not as deep a principle as integral as accumulation of a quantity, but still important for geometry. Okay, still important for geometry. So let's talk about finding the area bounded by y equals 5x squared and the x-axis. So can we sketch this curve by ourselves? Y equals 5x. So with these geometry problems, you have to have some savvy with sketching curves and functions in the coordinate plane. So you can't depend on your graphing calculator for everything. So this would be something that you might be expected to be able to sketch without your graphing calculator. So here's kind of a way of doing that. You could see this as factoring to x times 5 minus x. And right away that tells us what about the graph? What can we say about this graph now? Okay. Yep, so it's parabola, it's a quadratic, it's going to be a parabola. Is it going to open upward or downward? How do you know that? Negative x squared, this means it's going to open down. Okay, what else can we, now that I factored it into x times 5 minus x, how does that help us make this sketch? What does that tell us about the graph?
The 5 like a phase shift, either up or down or left or right.
Not quite, because it's multiplied by x. If every x was substituted with something like that, like x minus 5, then it would be shifting it. But this is 5 minus x times x.
What about how sharp the parabola is?
Nope. That's how like wide or steep.
Yeah.
So we're kind of less interested in that than more just getting a sketch. So that's more of kind of a fine-tuning detail. So we just want to get a sketch of this parabola. How does this help? Getting pre-calculus. Factored form of a polynomial. How can this help us sketch the graph? Zeros. Thank you, Mitchell. So what are our zeros? Zeros are 0 and 5. Meaning, values of x that make the function 0. Values of x that make y 0. And the factored form tells us that immediately, right? What values of x would make y 0? 0 and 5. And so if y is 0, then where are these zeros? If y is 0. On the x-axis, right? The x-axis, y is 0. So when x is 0, y is 0. Right? When x is 5, y is 0. And we said that negative x squared means it opens down, so now we can just make we're ready to make a sketch, right? If it opens down, it's got to look like this. Something like that. Okay, so I want the area bounded by this curve and the x-axis. So do you see what area that is? It's like the hill, right? The hump. So now we've talked about how can we, so you can't go, so here's the point. You can't go to a geometry textbook and go to the back set of tables and say, okay, find me what's the formula for the area of this parabola from 0 to 5? That right there, right? It's not going to be listed in a table of areas. But we have the tools now to do it. So what can we do? How do we get that area?
It's equal to the integral from 0 to 5.
Just like we just said, right? 0 to 5.
5x minus x squared dx.
Okay, now I want to show you something that seems like, at this point, seems like overkill, unnecessary, but it's what we want, the way we want to approach all of these problems, all of these geometry problems is going to pay big dividends down the road. So we'll just start practicing it now. So this one's easy just to write down the integral, but what I want to do is, let's think about those rectangles, right? Those rectangles were, I'm going to draw a typical rectangle or a typical strip. So that's what we're going to call it. So this is what I'm going to call a typical strip. Super thin rectangle. And that area really comes about by what? Adding up all the areas of all the typical strips. From what to what? Starting from, we imagine that first typical strip is like a point at 0, and then we're gonna stack them all up here, and the last one's going to be at 5. So what we're going to do is we're going to write the area of one strip. So what is the area of that strip? So base times height, right? Area is going to be base times height. What's the base? Yep, it's going to be our change in x. And what is the height of that strip? So from here to here, how high is that? Now this could be, I could have drawn this strip anywhere. So it has to be typical, meaning it's the height of any of those strips. So what is the height of that strip? Yeah, so some of you are saying it's the function. So in the simplest form, that the height of that is the y-coordinate of the curve. Do you see that? So really, the height of the strip is just dx times the y-coordinate of the curve, y. But if it's dx, then we're going to write the whole thing in terms of x. So what does y equal? Right, 5x minus x squared. Again, this feels really easy and redundant for this particular problem, but this is what we want to do when things get harder and we're getting to volumes and we have these hard physics problems. Sorry. Okay, so then this setup work, this is going to be our typical strip. So then what are we going to do? We're going to add all the typical strips up, starting at 0 and ending at 5. So this right here, that's one typical strip, the area of one typical strip, and we're going to add them all up from 0 to 5. So we don't. So the thing is, we don't want to just try to write the integral down at first. We want to kind of just look at one particular element and focus on one element and get what it is we want. A little bit of volume, a little bit of area, a little bit of work, whatever it is. A little bit of force, a little bit of pressure, and then get that typical amount, and then think about all the ones adding together, and then setting up the integral. Okay, so this is really easy. So we live for integrals like this now, right? So 5/2 x squared minus 1/3 x cubed, 0 to 5. So 125 over 2 minus 125 over 3, which is 125 over 6. So that's the area of that blue cross-hatched region, the area beneath the curve to the x-axis. Questions on this one? Yeah. Is it about the idea or the arithmetic? If it's about the arithmetic, let's just go on. You'll figure that out later. Is it about the idea or the concept?
The concept.
Okay, so we're
Why did 125 over 6 and not 5?
So
let's do the arithmetic later. Don't focus on arithmetic. Do you understand the concept? Let's focus on the concept. Trust me, 125 halves minus 125 thirds is 125 over 6. If you need to work that out later, work it out later. Okay, so do you have a question, Andre?
I think I figured it out. It was it's because we focus so much on dx times y that I was confused as to how we got to 125 over 2 minus 125 over 3, but then I realized.
I'm just plugging in, it's just evaluating a definite integral, right? I just did the antiderivative, plugged in 5. The zeros will be 0, right? Okay, any other questions? So now what about the integral from 0 to 8? So here's the picture of it from 0 to 8. What will that calculate? So if I did the integral from 0 to 8 now instead, okay, so now if we go back, good. So if we go back and thinking about it, instead of thinking about an area, go back and think about accumulation. What will it be? If this is the rate function, right? If this is a rate function, and we think about accumulation, what's the impact of this on accumulation? So tell me about the accumulation. If this is the rate, so what's happening to the accumulation now?
It's increasing.
Increasing. What about now? Increasing or decreasing? Still increasing, positive rate. Now what's happening to the accumulation? Decreasing at a negative rate. So in the end, do we expect a positive amount of accumulation or a negative if we go from 0 to 8? What would you say? Positive or negative? What would you guess? So the question is, what wins out, right? So we've got from 0 to 5, we've got this kind of low positive rate, and then from 5 to 8, we have this negative rate that gets, you know, significantly negative towards the end. So who knows? So who's gonna? So is the what is more, the amount of positive accumulation from 0 to 5, or the amount of negative accumulation from 5 to 8? Well, maybe it's close. Maybe I'm guessing the negative accumulation is going to win out. But so if you do this integral and you think about it in terms of geometry, are we going to get the area? Are we going to get the area of this area plus this area? Philip.
Yeah, I was going to ask you that. Like, since we already know what 0 and 5 is, could you set it up so that it's 125 over 6 minus whatever that is? Because after that point, it's all negative.
But I don't want to force it to be area. I want to ask the question, what is this integral going to give me in terms of geometry?
Oh, okay.
So what do you think it will?
It would give you the sum of that plus and that negative.
So it won't add up these areas. Is that what you're saying? It will not add up these areas. That integral.
No, I believe that it would. Or no. Wait a minute.
You just said.
Wait, I'm sorry. It would not.
So if it doesn't give the sum of areas, what does it give?
The difference.
Right. It's gonna. So areas. If I call this A1, when you talk about areas, those are always positive quantities. Okay. So maybe this is A1 here. We call this A1. Areas are always positive. So will the integral from 0 to 8 give us the sum total of area 1 plus area 2 as positive areas? Is that what that integral will give us? No. Thinking about it in terms of rate of change, we know positive accumulation and now negative accumulation. This is going to bring the quantities in this integral from 0 to 8. All this negative rate is going to bring this amount down. It's going to have a negative effect on it. Therefore, in terms of areas, how could we write this in terms of areas A1 and A2? What is this equal to?
Equal from 0 to 5.
Nope. I want to know what this equals to in terms of the areas, A1 and A2.
1 minus A2.
Won't this give us A1 minus A2?
Yeah.
If A2 is a positive amount of area, that integral is going to subtract out that amount of area. Just like when the rate is negative, it pulls the amount of accumulation down. Does that make sense? Really important concept. So the moral is that integral really, if we want to be precise, it gives difference of areas. The integral doesn't give areas, it gives difference of areas. Whenever that function goes below the x-axis, all those areas carved out below the x-axis are going to get subtracted from out of our final amount. Any areas that are created that are above the x-axis have a positive contribution to that integral, and any areas below will have a negative contribution to that area. So let's do it. So we want the integral from, what was it, 0 to 8? So let's do 0 to 5 first. Let's confirm what we had before. Was it 5x minus, no, x squared, what was that? 5x minus x squared?
Yeah.
Okay, is that what we got? Was it 125/6? Is that right?
Yeah.
Okay, so that's 125 over 6. That's what we got. So now, when we do from 0 to 8, do we expect it to be bigger or smaller than 20.8?
Smaller.
Because from 5 to 8, we're going to get a negative. It's going to pull this amount down by the opposite of whatever that area is, right? So, negative 10.7. So that amount of negative accumulation from 5 to 8 was greater than the amount of positive from 0 to 5. And the net result is negative 10. So what is the integral from 5 to 8? What would you say? So how would you find the integral from 5 to 8 then? Be something like negative, what? 30, right? So from 0 to 5, we get this positive area, 20.8. Then from 5 to 8, that area is positive 31.5, but it's below the x-axis, so the integral has a negative effect. So the net effect, or the net area, from 0 to 8 is a negative 10.7. Okay, so let's more practice here. Okay, so now, things like this, like I said, you should be able to sketch this region without a graphing calculator. So basic curves, y equals 1/2 x cubed, x plus y equals 6, and the y-axis. So what we want to do, we want to sketch the region correctly. Don't go on until you've confirmed that you have the right region. Then we're going to identify and compute area of typical strip. And then set up the integral to find the area, or difference of areas. This is an area, right? So this is an area bounded by these three things. Don't go on to number 2 until you're absolutely positively sure you have the right region. In my experience, students mess up the x-axis and the y-axis all the time. Know what the x-axis is. Know what the y-axis is. Know exactly what region this is defining. Don't go on to number 2 until you know you have the region right. Okay, stay focused on what you're doing. Look at your graded work later, okay?
It's like a weird flirt. Yeah, it kind of looks like a.
Yeah. Yeah, so like you got like that weird, just like bump right there.
Let's go ahead and talk about the x plus y equals 6. Here's the typical street. Let's go from the top of the x plus y curve to the 1/2 x cubed here.
Yes.
So,
Task.
the height, okay, so AS equals base times height, which if you look at the base as the 1/2 x cubed, and the number y, and the height as x plus y equals 6. I don't know how you end up really.
Well, in that where it's like the top curve minus the top curve, so it's like since x plus y equals 6 on top, so it's like x minus 6 minus.
You need 6 minus x.
Yeah, 6 minus x, yeah. Since we're using the y-axis, it's the x.
Not the right region.
Y-axis
Yeah,
is base, so
I saw you got that.
So you wanted
So I thought you were
x
looking at
equals
this
6
one.
minus y, and cube root 2y equals x.
Yes.
That's what what I'm saying is these big simple ones you should be able to sketch by yourself.
So then we
1/2
could
x
do
cubed and x plus y equals 6. Somehow you should be able to sketch those without
integral, integral from 0 to 6.
X plus y equals 6 is fine, right?
Okay, x plus y equals 6 is y equals negative 6.
Yes, if x plus y equals 6 was correct, then you'd have the right region, but x plus y equals 6 is not correct.
X values. So it's just like
So where's the region?
would be this.
So is it? No, that's I think of a way to do this is figure out what the point of the intersection between these two curves is. And you could just integrate using y as your coordinate. That first half would be integral of x equals cube root. Alright, so let's call this point A. Y coordinate A. So then you can set up the integral from 0 to A, and A is y coordinates. Cube root 2y dy plus the integral from A to see the linear curve goes into 6. So from A to 6. 6 minus y. Do you see what I'm doing? Like, so if we split that into half, into the two where we know what that is, and use y as our limit spin, y points as our limit spin,
Yeah, rather
and change y, and you're just kind of flipping, conceptually flipping the axis, but don't get it right.
Yeah, because the value here minus this value.
Makes it stable. That's how you make it stable.
When you go to a higher economic value, you start creating.
See how I solve the intersection? I always solve the intersection. That's you just set them equal to each other, right? And figure out what y is when
If I want to shrink it, I just go
they're
x
equal to each other.
Well,
It's a parabola. It's a parabola.
Oh, it's just a 2 and 4? Oh, okay, so y value of 4, so
It's not, because when you plug in, into here,
Yeah,
then
I
y
understand
equals 4,
that,
and
and
that's
you're starting with all that.
Totally right.
The 3 stays the same, 3 is always on x equals 3.
Okay, so then
But talking about the way it looks on the graph, if you've got x squared, then 2x is going to be narrower, and 4x, because they start to convert, they start to come to the y-axis, right?
so
Not in terms of x though, just the way they're shaped.
So right. So then
That's the point.
I definitely did this.
Oh no, I remember.
You multiply it
I just remember when it's the y-axis, which constitutes the
Because
top
y
and
is
bottom.
higher up,
Brutalize
so higher, so
those
it's
questions on the
So let's do this.
I'm trying to
This,
think
right?
in that sense, because like it's easy
Right.
to tell if like
So then
x-axis was
So
on
then
the
it's-
top or
Yeah,
the
that's
bottom.
not, yeah, that's not an issue.
all the y values are, but that's a little bit less important, like for this stuff. Like we
So I
want to
remember
just
Right.
I might still have like the exact problem.
Because you can have 0
There you go.
past
So now let's, you got what you have left, you have x plus y equals
x
6.
is second. Right.
Whenever the y was cube root.
I promise you, that's what
Zero to six.
Oh, I was like, no, I was like, what the heck? And I was like, no, no, I thought it was your wine.
No, this is already, that's like, that makes sense.
No, this is like wine. I was like, wait, are you trying? No, that's fine.
So, do we want to solve this?
There.
Yeah, it's just.
I haven't been a great
So
child,
let's-
but I really, I haven't memorized.
Integral 0.
Yeah,
Plus
see, all
integral
Because we don't actually need to just
And everything should be in terms of y.
Probably talking about
I'm thinking in the area, or just the area, I'm not sure like specifics. Even in terms of this.
The problem is that I'm making
something like this for anti-derivatives.
I was thinking something like that. I wanted to try a different way to see if like we would get the same. Because I want to see if like what I remember doing is the same as that. It's like since it technically doesn't ever get below the y axis, so it's convenient that one here we talk about curve.
Oh, I see what you're doing there.
Yeah.
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 So yeah, like your method would work too.
Yeah,
It doesn't actually cross.
Yeah.
Oh, they use
Just using different rate functions.
Yeah.
So this.
Okay, so compare your region with what I sketched. So lots of you got it. Lots of you got it. So y is 1/2 x cubed is this one, right? It goes through the origin at 0, 0. And then x plus y equals 6 looks like that. But it's a straight line though. So now I want to work on step 2. So I've drawn a typical strip, right? A typical strip. The bottom of this region is our y equals x cubed graph. And then the top is the x plus y equals 6. So a typical strip would go from there to there. So now what we want to find the area of that, an area of the typical strip. So what is the base? What is the base? What is the base equal to of the typical strip? Everyone with me now?
Yeah.
So whatever you're doing, kind of. So I want you to.
But I have a question. If you do that, then you have to evaluate from 0 to the intercept.
We're not there yet. We're just doing a typical strip. Yeah, we're getting there. We're getting there. Okay. So let's do one thing at a time. All right. So what is the base of the strip?
dx.
dx. And let's call it delta x to mean like a finite width, right? So dx we'll think of as a super small, and then when we're setting up a typical, we'll use delta x to mean, okay, so it's like finite. We can actually see the width, okay? So we can actually think of it as a rectangle instead of a stick. Okay, now what is the height of this thing? Is it just a y value like the last one? It's a change in y, right? So it's a change in y. So we have this, say, call this one y2, and then down here we have y1. So in terms of y2 and y1, what is that height? Right, so it'd be delta x times, it's a change in y. The height of that strip is a change in y. It's the greater y minus the lesser y, or the y2 minus y1. Do you see that? Really important, especially when we get into these harder volume problems tomorrow and Wednesday. Being able to do this is going to be really helpful. But if we're in delta x, that means we want everything in terms of x. So what is y2 in terms of x? What is the y coordinate y2 in terms of x? So we want, what is y? So that is defined by this line. So what is y in terms of x? 6, nope, y in terms of x. 6 minus x. So 6 minus x, then minus, what is y1 in terms of x? That's just our 1/2 x cubed. Are you following?
Yeah.
So that is that height of that typical strip. It's y2 minus y1. But we need them in terms of x because we have delta x. So it's going to be 6 minus x is y in terms of x for the top, y2. And y1 is simply 1/2 x cubed. And so that's our setup work for the typical strip. And now we're ready to write the total area equals. So what? We want to sum up all the typical strips from what to what? So this is what Ruth was talking about now.
0 to the intercept.
So is it going to be x values or y values? We're going to start at the first typical strip will be the left side, the x value at the left side of the region, which will be at 0, right? All the way until, so that at x equals 0, we imagine the typical strip right along the y-axis. And then we have all the strips added up until we get to, well, so the question is, this was the question Ruth was asking, what is that x value right there? So how do you find it? Yeah, we want the x value where the y's are the same, right? So for that point right there, the y of this is the same as the y of this. So what is that x value? So 1/2 x cubed equals 6 minus x?
Yeah.
So rather than try to solve a cubic, can we just kind of what? Just kind of trial and error this here. So what x value is going to give you the same for 1/2 x cubed and 6 minus x? Some of you are recognizing that it's 2, because you're going to get 4 in both cases, right? 2 cubed divided by 2 is 4. 6 minus 2 is 4, so it's going to be 4. Sorry, x is 2. This is the point 2 comma 4, which is on both of those graphs. So the typical strips line up vertically from x equals 0 to x equals 2. And so we're summing them all up. So it's going to be 6 minus x minus 1/2 x cubed dx. Done. So whatever that is, we won't, for time's sake, we won't do that. Anybody have a question? Okay, so same curves. We want the area now. Same curves, but x-axis. Y equals 1/2 x cubed. X plus y equals 6. and the x-axis. I'll sketch it again. So what region are we talking about now? Do you see it? Same two curves and the x-axis. You should recognize that we're talking about this now. So tell me about a typical strip now. For this region, what find the area of this region? Typical strip right here.
Would it be easier to convert the other one?
So the question is that a typical strip for this region?
It is for one part.
Hunter?
It is for one part. It's for the first part. 1/2 x cubed until you reach x equals 2.
Nice.
Instead of 2 separate.
Okay, so look. So this was that point we found before, 2, 4, right? So he said for the first part. So yes, this is a typical strip for x until we reach x equals 2. But then what happens after x equals 2? It's not the same typical strip anymore. That's why I have a different color. So over here, do you see that the blue strip and the red strip are actually different? What's different about the blue and the red? The top, the top of the strip, right? The bottom is the same, but the top is different. So what's this going to require to find the integral? 2 separate integrals. So typical strip for the red one, b times h, delta x, what's the h of that one? Just the y coordinate, right? And what's the y coordinate for the red typical strips? 1/2 x cubed, right? Boom, done. Blue. But now we have these blue strips. Also rectangular, delta x, also times y, it's just a y coordinate, because they both start from the x-axis, right? So they're just going to be a y, the height's going to be y coordinate. But what y coordinate do we have for the blue strips? Y is 6 minus x, right? And so the area is integral from 0 to 2 of 1/2 x cubed dx plus so that's 6, 0, right? So 2 to 6 of so we can still use an integral, but we need 2 integrals because the typical strip changes, right? It's first defined by the red one as the top of the curve, but then when we get to that intersection point, now the tops of the strips are defined by the top of the blue ones. Okay, but Ruth, you suggested something else.
I was thinking just that switching instead of being a vertical strip to make it horizontal.
Okay, so one thing we have to be good at, so we're not going to always use vertical strips. We can use a horizontal strip. So let's look at that. So I'll do that in black. So here, get rid of the red one. Okay, so horizontal strip would look like this, in black. So method 2. So the area of the strip is, can you set up the area of a strip? Again, it's going to be still a rectangular strip, base times height. But can you set that up? Okay, can you set up base times height for that strip? So let's keep the base as the thin side, okay? Base is thin side, height is long side, okay? So base will be thin side. So what will base be? How would we describe that right there? That's our base. So change in y now, right? So the base is delta y. And what's the height of the strip? Right, it's a change in x, right? It's a change in x. So you're going to have, I'll call this x2, x1. But if it's delta y, it's got to be in terms of y. So we need x2, this x coordinate, in terms of y. What is it? This is x2. Nope, x2 in terms of y. X equals what in terms of y? 6 minus y. Nope.
No.
X in terms of y. So x equals what in terms of y? 6 minus y. 6 minus y. Okay, x1 in terms of y. Now, cube root of 2y. Because we need x in terms of y. We're going to multiply by 2 and take the cube root. So, integral is? So now we're stacking up horizontal strips starting at y equals what?
0.
Yep, the first typical strip is at y equals 0. And then we're going to stack up all these strips horizontally until y equals, the last one is going to be up this point at y equals 4. And then it's going to be this thing right here with dy instead of delta y. Can't fit. So those two, the sum of these two integrals and this integral that we just wrote should give the exact same number because they're finding the same area. If you summed up these two integrals, 0 to 2, 2 to 6, and then you did this single integral from 0 to 4, stacking up these horizontal strips. Same exact result. And I would do it in the software over time. So for the before you pack up and run out of here, so before the to be ready for the homework, do you understand these two approaches to the same problem? And if not, ask me on the way out. Okay, ask me on the way out. It'll just be web work for tomorrow. Just web work for tomorrow.
Is there ever a time where you have to use one or the other? Or is it always like always both?
So yeah, so sometimes the functions are such that doing it one way will allow you to do an antiderivative, but then doing the antiderivative, you can't do it. So because of using antiderivative, it's like all these are easy because they're polynomials. But when you get into functions that result in harder antiderivatives, yeah, sometimes only one way works. Yep. I'll have a lot more work for you again tomorrow. All that stuff we handed in for the end of last week. I'll have all that back to you tomorrow. But ask on your way out. Otherwise, have a great night. See you tomorrow.